Hello, everyone! Today, we begin a fascinating chapter called We Distribute, Yet Things Multiply. What if a small change in one number could tell us exactly how much a product changes without multiplying again? Take 34 into 21. Increase 21 by 1, and the product becomes 34 into 22. Since 22 equals 21 plus 1, 34 into 21 plus 1 equals 34 into 21 plus 34 into 1 equals 34 into 21 plus 34. The product increases by 34, the other factor. This is more than a calculation trick. It reveals the distributive property. A into B plus C equals AB plus AC. A quantity can be divided into parts, multiplied separately, and then recombined without changing the total. Geometrically, a rectangle of length A and width B plus C can be split into two rectangles of areas AB and AC. Now increase both factors by 1. A plus 1 into B plus 1. Each part must multiply every part. A plus 1 into B plus 1 equals AB plus A plus B plus 1. The product therefore increases by A plus B plus 1. If one factor increases by 1 while the other decreases by 1, A plus 1 into B minus 1 equals AB plus B minus A minus 1. The change now depends on the original numbers. The same distributive relationship remains valid even for negative integers. The idea becomes even richer when the changes are m and n. The four terms are simply the four regions of the corresponding rectangle. Every term in one bracket meets every term in the other. This principle can make arithmetic surprisingly fast. Since 11 equals 10 plus 1, 5,243 into 11 equals 5,243 into 10 plus 5,243 equals 57,673. The shortcut is not magic, it is distributivity at work. The same idea extends naturally to numbers such as 101 and 1001. More than 1,000 years ago, Brahmagupta described this approach as multiplication by parts, breaking a quantity into convenient pieces, multiplying each part, and adding the results. Now consider a square whose side is 74 units. Write 74 as 70 plus 4. Its area separates into a 70 into 70 square, a 4 into 4 square, and two 70 into 4 rectangles. Therefore, 74 squared equals 70 squared plus 2 into 70 into 4 plus 4 squared. Replacing 70 and 4 with A and B gives A plus B squared equals A squared plus 2AB plus B squared. The 2AB appears because there are two identical rectangles. For a difference, begin with a square of side A and remove strips of width B. Two rectangles of area AB disappear, but the small b into b squared is removed twice, so it must be added back once. A minus b squared equals a squared minus 2ab plus b squared. Put these identities together and the middle terms cancel. A plus b squared plus a minus b squared equals 2 into a squared plus b squared. Another cancellation gives an especially useful identity. A plus b into a minus b equals a squared minus b squared. So 48 into 52 equals 50 minus 2 into 50 plus 2 equals 50 squared minus 2 squared equals 2,496. A long multiplication has become a difference of two easy squares. But algebra demands precision. For example, x plus 3 squared not equal to x squared plus 9. The correct expansion is x plus 3 into x plus 3 equals x squared plus 3x plus 3x plus 9 equals x squared plus 6x plus 9. The missing 6x comes from the two cross products. That is the real power of distributivity. Break a quantity into meaningful parts, preserve the whole, and let the hidden pattern emerge.